Good evening, everyone. I am Shomodip from Indian Institute of Science. I am doing my PhD here at the Department of Electrical Engineering at IISc. As a part of the teaching duties for the Prime Minister's Research Fellow Scholarship, I'll be taking these weekly sessions uh, with pertaining to your for clearing your doubts pertaining to the course titled Advances in UHV Transmission and Distribution, which is being handled by Professor Subba Reddy from our department in NPTEL. So basically, 1 week we have completed the for every week. I suppose there are 5 lectures which you have to see from the NPTEL portal every week, and then you have to submit some assignment, and based on your marks in the exam and your attendance and your scores in the assignments, you will be given a certificate from NPTEL. So today is the second week, and today we will be discussing of the from lecture 6 to lecture 10. Any doubts which you have, you can raise in between. So first, what I will follow is first 1 hour or first say 1.5 hour. I'll keep for uh, explaining some important concepts which I think has not been properly explained or due to lack of time. So I have identified some important concepts, and I'll be explaining that. If you have any doubt, you can raise your hand at any moment, or you can unmute your mic and speak. Is that fine? The course flow, is it fine with everyone? Can someone respond, please?
Yeah, it's okay.
Okay, fine. So I'll be starting. So first, I'll give you a brief outline of my screen is visible, right? The screen which I am sharing.
Yes, sir, visible.
Okay. So first, I'll be giving you a brief overview of what are the topics I'll be talking about. Means what are the lectures which has been covered in from lecture 6 to 10, and then I'll be taking some important topics which I think will be useful for you in the understanding of this course in a better manner. Okay. So the first topic in the NPTEL lecture series, if you can see, is so it is lecture 6. So what does lecture 6 talk about? It is the failure of electrical apparatus in the field. Importance of reliability and testing. So since this is a mostly a theoretical course, I won't be able to solve numerical problems. Uh, but I'll try to explain some important concepts which I think will be useful for you. Okay, so first, if you understand this topic, this failure of electrical apparatus in the field. So what do you understand by failure of electrical apparatus? So basically, as I described in the previous class, you need to understand this topic. You need to understand the basic philosophy of high voltage testing, the testing of different high voltage equipments which are commissioned in the power systems and the substations. So before commissioning them or before installing them in the power system substation, we need to undergo some important tests or laboratory experiments, you can say, which will give us an idea about the performance of that equipment when on field. So basically, the first equipment which comes to our mind, the most important equipment rather, is the transformer, which is the most costliest also. So a transformer, basically, if you see the insulation of a transformer, it is a composite type of insulation, right? So we have both solid insulation as well as liquid insulation. So I'll write the important points just. Composite insulation in transformers. So what are the composite insulation in our transformers? It is basically formed by oil and paper, right? So we call it as oil paper insulation in transformers. So you might think, I talked about the failure of electrical apparatus. Now why I am going to the insulation? So the most of the failures which are occurring in our transformers or any equipment, it is 90% of the failures are accredited to the insulation. It is due to the damage of the insulation. So the insulation is the most vulnerable part of a transformer or any kind of power equipment which gets damaged when a high voltage surge or a high current surge approaches that power equipment. So it is basically the monitoring of power equipments basically it boils down to the monitoring of insulation of a power equipment. It is the insulation that is causing the harm. So if we see if a lightning or a switching surge, it strikes a particular power equipment, the most attacked part or the most weakest part in a power equipment which will get damaged is the insulation, is the oil paper insulation of a transformer, or in case of our overhead insulators, it is the solid insulation which forms the basic design of that overhead insulator. So basically we need to provide some protective measures, we need to perform some tests rather to monitor the health of this insulation in the power equipment. So the insulation is the main thing which we need to take care as far as our high voltage test is concerned. Okay. Our oil paper insulation in transformers is composite insulation, and in our overhead insulators, we have the solid insulation. This is the solid insulation. Okay, it can be ceramic or the recent ones which are known as polymeric insulators. So the recent research in this field is going on in the development of new polymeric materials for this transformers or for this overhead insulator surge arresters. Because polymeric insulators, you know, it is more advantageous when compared to this ceramic insulators. The first advantage is that is the reduction in weight. Almost 50 to 60 to 70% there is a reduction in the weight. So suppose the technician or the lineman who goes on repairing these insulators, who goes on monitoring these insulators, he has to carry those insulators before installing or commissioning them on the actual power line. So a lineman or a technician, he will prefer obviously the lower weight insulators. So that is one of the biggest advantage of this polymeric insulators. Moreover, these polymeric insulators, the different kind of polymer mixtures we can use, and we can modify the breakdown strength. We can suppose we consider a particular mixture of chemicals and we prepare a polymer mixture, and then we use it to construct an insulator. So that will have a particular breakdown voltage. So like for example, SF6 and nitrogen, sulfur hexafluoride and nitrogen forms a good insulation mixture, and we can use that as a polymeric insulator. So research is going on in this field that what all new chemicals, what all new compositions we can mix them and generate a polymeric or a composite insulation, which will have performance characteristics more much better than the conventional ceramic or glass insulators. So these polymeric insulators are the recent trend or the recent research is going on in this field regarding the design of the material of this polymeric of the insulators. So this is one aspect, and the next thing. Now you need to understand what is reliability or testing. Okay, so what is reliability? The basic English word, it gives us a feeling that our tests, the experiments which we are conducting, should give, suppose I'll explain it like this. Suppose a utility person gives you 10 insulators he has manufactured, and as a high voltage engineer or as an electrical engineer, he gives you and tells that this my insulator, you test it and give me a certificate that yes, it can withstand this much amount of voltage, this much amount of current, both for DC and AC. He will ask it. So what is your job? Your job is you have to take these insulator pieces and then you have to you have to perform certain tests which I'll be describing today, the basic high voltage tests, and you should assure him by providing a proper certificate that yes, your equipment which you have given, it will perform, it will withstand this much amount of voltage on field. So how you will give that assurance? That is what lies in the basic philosophy of high voltage testing. So what is reliability? From the word itself, you can understand the reliability and safe operation of any electrical equipment. It will depend on the integrity of its insulation. So this is the reliability, or means you are being reliable to that person. That person is trusting you, the utility person. He's giving you a set of insulators or a set of equipments, and he's telling that you tell me how much voltage it can withstand. So to understand this, you need to understand what is a high voltage test and what is the performance of, what is the main goal or the main motto of doing that high voltage tests. So high voltage test, what we do is we deliberately apply slightly higher voltage to the equipment than its normal working voltage for a specified period of time. Suppose I get a polymeric, I prepare a polymeric insulator, or suppose utility person gives me a polymeric insulator, and we deliberately apply. Suppose we know that it will, he will tell me what is the normal working voltage. So suppose he tells me the normal working voltage of the insulator is 11 kV. So deliberately I will apply at least 17 to 20 kV, at least 5 to 10% more voltage, and see whether it is flashing over or whether it is withstanding it. So if I can give him the assurance that yes, your insulator can withstand 17 kV or 20 kV. So he will be assured that yes, under normal working voltages, obviously this will work fine. And even if there is some drop, some rise in voltage due to some issues, then also my insulator will work fine. So that is the main goal of this high voltage test. So it is the deliberate application of a slightly higher voltage to the equipment. So the basic deliberate application of slightly higher voltage to the equipment than its normal working voltage. Correct. So, so what is the purpose of an HV test? Its purpose is to guarantee that the equipment has met the desirable dielectric strength. So it is this dielectric strength which determines the performance of the insulation. So it is a, say, a quantifiable term or a quantifiable parameter by which we can say that yes, your insulation has met this requirement. Okay. So now you need to understand the basic philosophy. So anyone wants to ask any question, you can stop me in between. Whatever I have explained, if you want to ask any questions, you can stop me in between. Fine. You can unmute your mic and speak. So what is the basic philosophy of high voltage testing? So for this, you need to understand what a high voltage test is expected you to provide. It should be a high voltage test should be a reasonably simple laboratory test involving a reasonable time. Like your test cannot continue till 1 year, 2 year. It should be completed within a stipulated amount of time, which can give reasonable assurance to the utility person that I have written just in whatever I have understood, I have written it that the equipment will give satisfactory performance. So whatever I have explained till now, I have written it down. So now, what it should simulate? Like I'll give you an example, so it will be easy for you. So I was talking the other day about the pollution tests on a high voltage insulator, right? So why we perform the pollution tests? These high voltage insulators near the factories and all near the chemical, it will be installed everywhere, right? On the transmission lines, it will be hanging. So suppose it is near a chemical industry. So different chemicals will be deposited on it. Even some birds will sit on these transmission lines. And as you all know, these birds will not get shocked because both their legs are on the same potential, are at the same potential. So no current will flow. Hence they can easily sit on these transmission lines, this bird. So these bird droppings will also deposit on the surface of the insulator. So these bird droppings or the excreta of the birds, if you analyze it chemically, it has been found that some conducting materials are there because ammonia is present there. So this will obviously alter the conductivity of the performance of that insulation. So that we need to simulate. We need to understand what is the chemical composition of the bird droppings, and then we need to simulate an identical condition in the laboratory, and then we need to understand how it is performing and how much buffer we should give, how much extra voltage it should withstand. Suppose the working voltage is say 10 kV. So I need to design my insulator not for 10 kV because of these unexpected pollution conditions or some air pollution, some chemical depositions, some bird dropping depositions. We need to give some voltage buffer because it will obviously be conducting in that situation. And so we need to understand all these things and we need to perform the similar experiments in our laboratory, and then we need to understand. So a high voltage test, it will simulate HV test will simulate one of the following. So number one will be, it should be prepared for the worst case situation. So theoretically, we should understand what can be the worst case voltage appearing across that insulator. If what can be the worst case maximum voltage or the maximum current which is appearing across that insulator, and our insulator should be tested for that kind of voltage path situation, and it should be able to withstand that worst case voltage. Yes, obviously failure will come. Obviously, even after installing the insulators, even after performing all kind of tests, type tests, sample tests, routine tests, then also our insulator will fail. Yes, that is correct. But we need to be prepared. At least we cannot predict the nature, right? But we need to be prepared for the maximum worst case voltage. If due to some condition or the other, if a voltage surge comes which has magnitude more than our prepared case, obviously the insulator will fail. But it will not happen every time. With experience, high voltage engineer, he will understand what can be the maximum voltage. Understanding this maximum or the worst case situations in the field, that requires more of a practical knowledge. So in theory, we will analyze what will be the we can analyze the different cases where a lightning strikes say our phase conductor or our ground wire or our insulator. So if what will be the voltages appearing? We have a rough idea of what is the voltage or the charge associated with the lightning, or what is the charge which is being brought down from the clouds to the ground by a lightning strike. So from that we can analyze and suppose a lightning strikes one of the phase conductors. So obviously the light, say it is a, that will be a case of indirect strike to the insulator. If a phase conductor, it is strikes a phase conductor, obviously there will be traveling wave phenomena and the voltage surge will obviously travel to the insulator. Maybe there will be some deflections. We need to analyze all those things and we need to be prepared for that. That is one thing. And we need to be also, as I was talking, we should be prepared for imaginary severe situations. Imaginary, but sensible. Is everything clear to everyone? Any doubts? Any doubts? You can raise your hands. Anytime you can stop me in between. Fine. Imaginary but sensible severe conditions. We should be prepared for that also. So this is our worst case situation as I was talking. Based on analysis, we can understand what can be, or based on different previous different incidents, we can understand what is the worst case situation. But apart from that, we should also be prepared for some imaginary conditions. Like this has not happened any time before. Yes, Mr. Purushottam, you have some doubt?
Sir, excuse me, sir. The screen is not updating, sir. It's hanging in between.
Oh, is it updating now?
No, sir.
Which screen you are seeing now?
Sir, actually, basic philosophy of high voltage testing and HV test will simulate up to that only I am getting, sir.
Two conditions you are not getting now, red colored.
Yes, sir. Yes, sir. Now I am getting, sir. Thank you.
Yeah, maybe
you, sir.
some issues in the now. Is the slide changing now?
Yes, sir. Yes, sir. Now it's changing, sir. Thank you.
Okay. Okay. Any doubts you have? Anything?
No, no, sir. No, sir.
Okay. You can lower your hand. Anyone has any other doubts? Anything? Please ask your doubts. Otherwise, these sessions will be of no use. I'll just keep on talking and I'll not get whether you are understanding or not. You have to ask some doubts at least. Fine, I'll continue. You can stop me in between any time if you want. Fine. Okay.
Yes,
So,
you can continue.
okay, okay. Who was that? Anything you were asking?
No.
Anyone?
No, you can continue.
Okay, okay. Thank you.
Okay.
So now we need to understand. So how we will test this quality of laboratories testing. So there are different high voltage laboratories, different small scale, medium scale, large scale high voltage laboratories, which are present throughout the world in our country also. So now how will you understand? So basically, as an utility person, how will you know that yes, I can trust this laboratory? The test result of this laboratory can be trusted. So how will you understand that? So for that, we have some parameters. Basically, three parameters are there. So I'll just explain those. So the quality of high voltage lab tests can be understood by number one is repeatability. Number two is reproducibility. And number three is representativity. So these 3 R's. Just a second, I'll be back. Okay. So I was talking about, yes. So how will you understand how this lab test, this HV lab test, the quality, how it can be understood or assessed? So first is there are 3 R's basically. So for that you can understand it is repeatability, reproducibility, and representativity. So you need to understand each else. So what is repeatability? Anyone, any idea what is repeatability?
The test result should be repeatable.
Can you speak a bit louder, Samir?
Yes. Can you hear me now, sir?
Yes, yes.
Yeah, the results should be repeatable. Whenever we do the similar test, we should get a similar reading.
Yes, correct. So repeat any laboratory experiment, not specifically pertaining to high voltage laboratory test. Any experiment. Suppose you get today, you are doing today at 6:38 p.m. You are doing your experiment in your laboratory and you are getting some result and you are very happy with it. Tomorrow morning, when you come, suppose you do the same experiment and you get a different result under the same identical laboratory condition. This can happen. So then you will say that your result is not repeatable. That is, your result is not repeating every time. So that result cannot be accepted. So this repeatability, it is the ability to produce identical results every time. Okay. So basically what we will do, we'll do this testing. Suppose I do it today, today evening I do it 6:40 p.m. and I get some result, I keep that. Again, after 1 or 2 hours, again I do the same result, same experiment. So now suppose you are getting the breakdown voltage of the insulator at 6:40 p.m. you are doing and you are getting the result at say 7 p.m. You are getting it at 10 kV. So now the next time when you do say after 2 hours or tomorrow morning, you will not get exactly 10 kV. You will get 10.1, 10.2 like that. So there is a certain percentage by which within, if the result is within that, then we can say that yes, our result is repeatable and the first criteria is passed. So all these things you have to you have to tell the manufacturer or the utility person when they give you the insulator and when you give them back the certificate, you have to tell them how many times you have performed, what are the breakdown voltages, and then you have to conclude that yes, my result is repeatable. So you can understand, you can trust my result. So everything is made public. Okay. So now reproducibility, right? Reproducibility is it is also similar.
Yeah,
Hello?
excuse me. One question. Yeah, one question.
Yes.
Repeatability, we are doing the test in the same laboratory, correct?
Yes.
Okay. Now the customer is getting the result. Okay. Now suppose he is going to some other lab, he's getting some other results. That case, do we say is repeatability
No.
there or not?
That is what I'm going
No.
to explain. That is reproducibility.
Okay.
If you are doing in a different
Okay.
lab, that is reproducibility. That is not repeatability.
Okay, fine. Okay. Okay.
Okay. So repeatability is the ability to produce identical results every time in one particular lab. And now, if you go on and perform the experiment in a different lab, so that is called reproducibility. So that is, it is similar to repeatability, but it is the ability to produce identical results in any lab. And what is represent? So you understood the difference between repeatability and reproducibility, right? So your experiment should be performed in at least 2 or 3 different labs, and it should give you identical results. Fine. So representativity, it is the ability to duplicate the field conditions. So this thing is not possible in most of the Indian laboratories, but in the foreign, this is a representativity is taken as a criteria for assessing your laboratory testing. So this type of these labs which can assess the representativity of a particular laboratory test are very few across the globe. And the representativity test could only be carried out if the particular lab is equipped with that kind of arrangement where we can duplicate our service and field conditions. So these are the basically 3, or rather for Indian labs, we will say there are basically 2 R's, or repeatability and reproducibility, which we need to understand, which we can use as a parameter for assessing the successfulness or this trusting issue with our particular laboratory test. Okay. So these were the
I have
things.
one doubt.
Yes.
See, repeatability, you are saying that suppose insulator, you are testing it in the evening, and it is 10% more than that of the standard normal voltage. When you are doing the same insulator on the second day, because you are done some the voltage you applied extra 10% more, therefore the insulator, the property itself will do this one slightly it will be less because you are tested it at a higher voltage.
No, the working
Therefore, the
conditions will
property
be
is
same.
deteriorating it. And the next day when you are testing it, certainly it may fail, it may not give the same result.
Can you come once again, sir?
Suppose you are doing the first test and you are doing it slightly higher voltage, that is 25% or 30% extra. When you are doing exerting a higher voltage, the property of the insulator, it will get deteriorated. And the next day when you are testing on the same insulator and the same voltage it is there, the insulation already deteriorated. The same results you cannot get it, no?
No, actually the thing is, these tests, when we will do it in the lab, first we will check how much voltage it can withstand. What is the working voltage? Say the working voltage for the insulator I have designed is 10 kV. So I'll be testing it for say 20 kV or 15 kV. So you are saying that it will deteriorate, right?
Yeah,
because of the
yeah,
application
right.
of this higher voltage.
Yeah.
So that will not
certainly be deteriorated. And the next day when you are doing it, because of the deterioration, it may not withstand the next day 15 kV. It may fail.
No, the thing
it
is,
may fail.
no, the thing is actually, we do it when we do it. If it passes the test or if it doesn't flash over, there is no significant deterioration in the condition of the insulator or the performance of the insulator. So if it is withstanding this 20 kV, so one particular set of experiments when we are doing, we'll do it for say 10 times. And again, tomorrow we will do it for another 10 times. So is it
many times if you are doing it, naturally the property of the insulator may not retain the same.
Right. So insulator property is it is good. A good insulator, I think not much deterioration.
That's what I'm
Otherwise,
thinking.
yeah, weak means it will fail, sir.
If it is very weak, then only if it fails or if it flashes over, then the story is finished. We are not going to test it any further. But the thing is what you are telling, even if it passes, there will be some deterioration in the quality, in the performance of the insulator.
Yeah.
But that will not, whatever I know, as per my knowledge, that will not happen. The significant deterioration will not be happening, so that it will, so that it will deteriorate my further future results. So that
No,
much
no, it is just
deterioration will
what
not
I
happen.
say is it's not the failure. It is just the repeatability means the same test results, it may not repeat because of the insulation, it had deteriorated.
Hmm.
The flashover would not taken place. But the repeatability, the same voltage and other parameters, it may not retain because the insulator, it would have deteriorated its property. Therefore, when you are doing the same on the same insulator, I don't think it will be repeat, the same characteristics will repeat. It will have a different once it is tested.
So there is some means exactly same we don't want. Suppose today evening we get it 15 kV. Next morning we don't want it. There will be a band of tolerance, obviously. So that I am telling that will not be as significant as you are thinking. Maybe due to this deterioration, there will be some performance deterioration in the insulator also, but it will not be as high because there is a tolerance band within which my result should be there, so that I can declare it that my test is repeatable.
Okay, if that is a tolerance
right.
is there, yeah,
Yeah, tolerance is like there might be.
then it is repeatability we accept.
Yeah, might be 1% or 2% deviation that is allowed.
Okay.
Yeah, right.
Now, since you are saying repeatability, it is exactly it has to repeat means it will not repeat. That's sort of
No, not
doubt
exactly. Exactly,
yeah.
nothing will happen. Exactly, it
Right.
cannot happen. There is some tolerance band within which our result should be.
Okay, fine. If it is within the tolerance, it is acceptable. Right.
Thank you. Thank you.
Okay, thank you.
So now you need to understand, we are done with the quality of what are the different tests. So now you need to understand what are the different things which are causing the failure of electrical apparatus. So there are different kinds of stresses. Number one is electrical stress, as we are all talking about. Apart from electrical stress, so under electrical stress, what we have lightning, we have switching surge, lightning surge, and switching surge. We have lightning surge and switching surge. These are the main kinds of over voltage electrical stress. You can also call it as over voltages, right? So these are the two types of voltage. These are two types of over voltages or surge voltages which can appear across a power equipment, which can damage it. So apart from electrical stress, we also have mechanical stresses. So when can a mechanical stress happen? Suppose when you are transporting the equipment, suppose your manufacturer from the manufacturer, you are transporting the equipment to be tested or to commission it in the actual power line. So during that time, there can be some fracture in the equipment, some stress can appear, some mechanical things can happen. Anyone has any doubts? I think someone has raised the hand. Yes, Mr. Purushottam.
Sir, my doubt is, sir, why actually one term is called type test. The type test is different from these tests, sir.
No, I'll be discussing about all these things. Type test, there are different categories of high voltage tests. So in that, one is type test, then we have sample test, and then we have routine tests. So all these high voltage tests will come under different categories, which I'll be discussing it later. It is in the next lecture, I think.
Okay, sir.
Your voice is not audible, Mr. Purushottam.
Okay, sir. Okay, thank you, sir. Understood.
Okay, thank you. So this mechanical stress that can happen during transport of this raw materials or during the transport of this manufactured equipments. It can happen during packing, loading, during unloading, moving to final location. Due to the while even during the service, there can be short circuits and there can be some electromechanical forces which can cause this mechanical stress. So these are the different types of stresses. The two stress I talked. Next will be the temperature. Am I audible? Hello?
Yes, sir.
It's audible.
Okay. Okay. In between some disconnection happened. Okay, fine. So we have the temperature stress. That is under normal the normal working conditions. Say we we manufacture an insulator. During the manufacturing process, we will not know where it is being commissioned. There is a huge temperature difference across our country, across different places. So suppose we manufacture insulator which can the performance which we have shown, which we have predicted based on the tests, that will only be applicable, say, at the temperature of West Bengal. Say Kolkata temperature, it will withstand 30 to 35 degrees centigrade. But suppose if that manufacturer goes on and installs that insulator in a part in the Rajasthan, the westernmost part of the country, where the temperature is very high, around 52 degrees centigrade in the summer. So there it will not obviously work. Again, if he goes on and installs that at Kashmir, where we have snowfall every time, temperatures going beyond 0 degrees. So there it will not work. So it should be also prepared. The tests should also be done pertaining to the uh, temperature of the surroundings. So due to high temperatures, what can happen is local hotspots can form on the equipment. Local hotspots on equipment. This is one of the damaging factors which will happen due to the temperature. So we have other different ambient conditions which will affect the insulating strength of an equipment. Like we have anyone can explain what are the different other ambient conditions on which the breakdown voltage of power equipment will depend?
Moisture content,
Sir, fog,
Wind and
pressure,
ice.
Mr. Fog.
Uh, the humidity and moisture content. That is,
Wind.
the humidity and moisture content is one of the deadliest conditions which can affect the insulation. So while breakdown, while studying, hello, yes,
Pollution also. Pollution.
pollution, correct. So it is the humidity and the moisture, right? Humidity or moisture in atmosphere. Then we have dust and chemical deposition on the insulated surface. So these are the different ambient conditions. So the four different kind of stresses or due to the which can cause the failure of an electrical apparatus. So those are the electrical stress, mechanical stress, temperature stress, and the stresses due to the ambient conditions. So this humidity and moisture in the atmosphere, the normal humidity or moisture in the atmosphere is how much? Any idea, anyone? What is the normal moisture content in the atmosphere in the standard temperature and pressure conditions? Any idea? Any idea, anyone? What is the normal humidity? What is the normal temperature under standard temperature pressure conditions? What is the normal temperature?
Normal temperature will be around 28 to 30 degrees.
It is 27 degrees. Sir.
27,
Under standard
30.
temperature pressure, we consider it as 27 degrees. What is this pressure, atmospheric pressure? What is the normal atmospheric pressure? Any idea? So the normal temperature is taken as 27 degrees centigrade or 300 kelvins, and the normal pressure we consider as 760 millimeters of mercury, right? That is the standard temperature and pressure. And regarding humidity, it is 11 grams per cc. That is taken as standard humidity of atmosphere. Anything above or below it, we have to apply the correction factor. Standard humidity of air. And so STP conditions will be 760 millimeter of Hg and 27 degrees centigrade or 300 Kelvin. So anything above or below it, below this temperature and pressure and humidity, that will cause a difference in the breakdown strength of that insulating surface of the insulator. Correct. So these are about the different stresses. So now, as Mr. Purushottam was talking, we'll be talking about the different classifications of high voltage tests. Right. So number one is type test. Then we have the routine test. And next we have the sample tests. So type test, that is basically done to verify or to understand the main design characteristics, and it is done normally for few samples on a small number of samples only once for a new design. Suppose a new design of an insulator is made and we perform the type tests to on a small number of samples. Say there are 100 insulators. We take some 10 insulators, say, or 15 insulators, and we perform the test on that insulator on that 10 or 15 insulators, and then we perform our type tests to check whether it meets the main design criteria. Next, we have the sample tests. So what are the sample tests? So sample tests will be done. These insulators will be taken at random from a lot. So insulators will be taken at random from a lot. We have a lot of say 100 or 200 insulators, and we pick up say 10 or 20 insulators, and then we verify the characteristics of the insulator that can vary with the manufacturing process. So during the manufacturing process, we throw the insulators, we transport the insulators from one place to another during the manufacturing process, and then the commissioning of the installation process. So there can be various damage in the insulator, or some particular performance of the insulator can be compromised, might have been compromised. And using the sample tests, we basically try to analyze whether what all performances have been modified. What all performances have been modified during this manufacturing process. Okay. So then we have the routine tests. So routine tests are done as a routine, as the name suggests. These routine tests yes.
My humble request is, you said it is some samples out of some type test also, some samples are taken and it is being tested. Suppose a transformer is there. Suppose it is designed a 10 MVA transformer. Can we subject it is a 2-3 transformers? A type test. It is only one transformer, it will be subjected to a type test.
Yes, I was talking from the perspective of a overhead insulator. Yeah, for transformers, obviously one transformer will be tested.
So it is depends upon the cost of the equipment. Either it will be a single or it will be a multiple.
Yes, correct. Thank you, sir. Thank you for the correction. Yes. So as I was talking, this type tests from the perspective of overhead insulators, I was talking that some multiple insulators will be taken, And but for a transformer, depending on the cost of the equipment and the cost of the equipment, a single equipment can also, a single piece can also be tested, as it was correctly pointed out. Yes. So going back to the routine tests, as the name suggests, these are the tests which are performed on each and every equipment. Means in a lot we have, there are 10 or 15 lots, and we perform this routine test on each and every insulator. I'm talking all this from the perspective of our overhead insulators. And these tests are performed on each and every insulator, and it is performed basically. So if we manufacture say 500 or 1000 insulators, so obviously due to human error or something or the other, there will be some defective pieces also during the manufacturing process, due to shipment, due to transport errors, telling. There will be, and these routine tests are performed to eliminate such defective pieces. So what are the different routine tests? So the first is a mechanical test to test the mechanical strength of that insulator. Then we have the electrical test to test the voltage withstand capability of the insulator. Then we have a visual inspection test. So as the name suggests, this visual inspection test means just by seeing the insulator, we want to understand whether it is okay or whether it is a defective piece. And if it is a defective piece, we straight away reject it. So this is the routine test. So I'm explaining it in just briefly. If you have any questions, anything, you can ask me. So this one of the most there are some other special tests also which doesn't fall in this category of type test, sample test, and routine test. And one such test which I want to talk is about the accelerated aging test or the pollution test. So what is an accelerated aging test? So this age of this power equipment is very important, because we want to understand, we want to see how many years this equipment will be able to perform, perform on service. So basically we do this accelerated aging tests by performing a series of aging experiments. Or the accelerated terms comes from the from the fact that so these accelerated aging tests are performed, and we have the pollution tests, the corona test, the voltage distribution test on the string insulators. Then we have the RIV or the radio interference voltage tests on these insulators, because this mostly these power lines will run close by or nearby to the telephone communication lines also, and there can be some interference from these communication lines which can affect the performance of these insulators. High frequency. So we basically in RIV tests, basically we test it with the high frequency component, and we see what is the performance of the insulator. Okay, so this is all about this failure of electrical apparatus. Now I will move to an interesting topic. So next is in the 7th lecture, you will see that there is a topic on the field computation, the numerical field computation. So I'll be talking of the different numerical field computation techniques. Why we need field computation, why we need to compute electric field, magnetic field, all these things I'll be talking about. And if you have any doubts pertaining to that, you can ask. So first of all, in the field of high voltage testing, why we need field computation? Why we need to compute the electric field? Any idea?
Electric field is electrical stress, volts per distance.
Yes, correct. So as I was talking the other day, anything means any stress which any equipment is experiencing, it is not because of directly the voltage. It is because of the electric field. Electric field is a kind of electrical stress which is occurring, which is causing the harm. So this electric field, what is basic electric field equation? It's basically given by voltage by gap distance, right? So if you have say the simplest geometry which we can think is a parallel plate capacitor. We apply a high voltage on one of the plates and we ground the other plate. So field computation, which you have learned, suppose we have This I will come later. So suppose you have a point charge Q and say you have a point P, which is say this is x1, y1, z1, and this is x2, y2, z. So this is the particular coordinate of that point charge, and we have a point P here. So if we want to find, and electric field is a vector, right? So what will be the expression for electric field? Anyone can help me out? What will be the electric field due to this point charge Q at P in vector form? Someone has to tell, otherwise this is going on boring.
Q1, Q2 divided by 4 pi epsilon the R square.
How much? Can you come once again?
Q1, Q2 divided by 4 pi epsilon R square.
What is
What is the
Q1? What
distance?
is Q2? There is only one
Q1
charge.
charge.
What is Q1 and Q2? Can you tell?
Only one point. Yeah, I'm sorry.
One charge is there and we want the electric field at one point. How you will calculate? Can you tell?
I'm sorry.
Yes. Anyone can please tell? What is the electric field? This is basic class 12 thing.
It is P dot Q divided by D squared.
Can you tell once again?
P dot Q divided by D squared. That is D squared means that is a vectorial. That is x1 minus x2 plus x.
Okay. Yeah, you're correct. Maybe you're telling it some other way. Anyone else? The normal vector form in terms of the distance between these two. Okay, first you tell me the scalar form you tell. Suppose this distance I am also giving, say it is R. Now you tell me what is the electric field at P.
P dot Q divided by R squared.
No, I'm telling the magnitude only. Where is the?
Since you are asking a vector, it's a magnitude means PQ divided by
No, P
R
is a
squared.
point. P is a point.
No, P is the point. It may be this one, a unit charge.
No, no.
See,
Q
suppose
is
you
the
want to
Q is
understand the
the Q
potential.
is the charge. Q is the point charge, and P is a point where you need to find the electric field.
Electric field in the case we have to bring a one unit charge and
The electric field due to a point charge formula, none of you know. So what you are telling, can you please write it down and post it in the chat? I'll call by some names. Someone has to answer this. What is the electric field due to a point charge Q? Dr. Valsalal?
I
Any
think
idea?
it's yeah, Q by 4 pi epsilon naught R square.
Yes, correct.
Q is the charge of that particular point.
So magnitude is Q by 4 pi epsilon naught R square, right?
Yeah.
Okay, fine. And if we want to express in terms of vector, what will be the answer?
We'll be getting unit vector R.
Correct. R cap, right? We represent it like this.
Yeah.
So if we try to expand it, I'm representing this 1 by 4 pi epsilon by K. Okay. Every time I don't need to write it. So it is KQ by R square into R cap. Again, we can simplify it. What is R? What is the unit vector? How can we represent it? Any idea? I'll go by the name. Abhinaya, can you come out? Can you please tell me what is this unit vector? How we can write it in terms of the original vector? Samir?
Sir, I don't remember it, sir. It's very long.
Okay. All of you are some of BTech students, right? So basically we write it as R vector by magnitude of R vector, right? So if we simplify it, what it will come? Is it correct? KQ by R cube into dot the R vector, right? So I think you have some doubt. I'll do one problem. You try to understand this first. Suppose I have 2 microcoulomb charge and I want, suppose it is at 0, 0, 0. I want the field at 1, 1, 2, 3. So using this formula, can you find out what is the electric field at P due to this 2 microcoulomb charge? Anyone? Dr. Valsalal, you can try it out. Anyone can try out what are the, how you can just tell me the procedure, how we can calculate the field. First of all, tell me how we can calculate P. So we want this E at P KQ by R cube dot R vector. So K we know it is 1 by 4 pi epsilon. Q I have given you 2 microcoulomb. So what we need here is R, right? So what is R vector here? Can anyone tell?
Yeah, the slide is not moving. Yes.
No, it is not moving. Now, can you, which screen you are seeing?
No, downside. Same, right? Just lift it up.
Yes.
Yeah.
Yes, can you tell me how we can find out R vector here for this problem? Dr. Valsalal, can you tell?
I'm trying.
Okay. So all of you are from electrical engineering background, right? Don't search it in the internet and tell me if you can tell, you can directly you can tell me. Anyone? Samir? Mr. Raju? Purushottam?
not able to recall.
Okay. This
Because,
R unit vector.
the unit magnitude
Just-
may be unity,
Yeah,
magnitude may be unity, but the direction it is
Oh,
it is a
how you are telling the magnitude will be unity? The distance between this 0, 0, 0 and 1, 2, 3,
because
how
the
it will
R
be
you have
unity?
taken it because the R you have taken it out, therefore the magnitude it is removed. Now only the unit the vector, it is a unit vector, means it is a 1. Magnitude is 1, but the direction is there. The direction, it is in the 3 coordinates we have to make it.
1 second, 1 second. So how is which is the unit vector? This R cap is the unit vector, right? This one. This is my unit vector, right?
Yeah, that is right.
Correct. So now this is not my unit vector. I have changed it. This is my actual vector, right? This is my actual vector. Okay. Point investing time. I'll tell you how to find the unit vector between 2 points. So it is basically the difference between the coordinates. So if I change here, what will be R? 1 point was here, say 1, 2, 3. Another was here 0, 0, 0. What is the unit vector between these two? So in calculation of field, basically what we take is source minus destination, right? Or it is destination minus source, sorry. So what is my destination here and what is my source here? My source is the point charge, right? So the point charge is at 0, 0, 0. And my destination, I'm trying to find the field at P, which is at 1, 2, 3. So basically my destination minus source. So it is 1 minus 0 into I cap plus 2 minus 0 into J cap 3 minus 0 into k cap. So it is I cap plus 2 j cap plus 3 k cap. Is it clear now? What will be the
Yeah, it's
magnitude
okay.
of? Yeah, what will be the magnitude of this vector? Hello? What will be the magnitude of this vector?
Square root of 1 square plus 2 square plus 3 square.
Correct. There is also many people. That is square root of 14. So what will be EP? It was KQ by magnitude of R square into R vector, right? So K, I am keeping it as it is. So K is 1 by 4 pi epsilon is how much? It is 9 into 10 power 9 into 2 into 10 power minus 6 by square root of 14 whole square means 14 into I cap plus 2 j cap plus 3 k cap. So it is basically 12, 18, 18 into 18,000. So I can simplify it. So into I cap plus 2 j cap plus 3 k. Is it clear? Any doubts?
Yeah, it's okay for me.
You have understood the field due to how to calculate the field at a point due to a point charge, Samir?
Yes, sir. Yes.
Clear, right? Okay, fine. So this is this we can calculate this why field computation is necessary. I have told you. Now we will talk about the different ways of field computation. So what are the different ways of field computation? There are basically two methods by which we can compute electric field. Two broad ways. Anyone has an idea what are the two broad ways of field computation? One is analytical field computation. Another is numerical. Can you tell me what is the difference between these analytical field computation and numerical field computation? Any idea? Any idea, Dr. Valsalal?
Yeah, analytical field computation is some empirical formula or any mathematical equation. Numerical field computation is software and like software.
Correct. So numerical field computation need not necessarily be a software. We can develop our independent codes or independent programs for that. Can you tell me some of the numerical methods which we use for field computation? Any idea? Anyone?
Simulation method.
Yes,
Simulation
yes.
method.
Yes. Charge simulation method. Anything else?
I think finite element method.
Correct. Okay, fine. I'll write it like this. 1 second. So numerical field computation, we can subdivide it into two parts. Okay. So first part is one is called boundary based methods. Another is domain based methods. So basically, suppose you have an electrode shaped like this. I'll explain you the difference between boundary based and domain based. Okay. Suppose you have a spherical electrode, two spherical electrodes, say. This one we are applying a high voltage. This one we have grounded. Now, I want the electric field at any point in the space. So how will you do that? So if we use so first you need to understand why we want to do numerical. So the basic difference between numerical field computation and analytical field computation is, so this analytical field computation, this can only be applied where we have a particular shape, a particular empirical formula which is well established for that particular kind of geometry. So basically we cannot develop empirical formulas. Like for a point charge, we have an empirical formula for electric field. For a line charge, we have an empirical formula for electric field. For a spherical charge distribution, for a volume charge distribution, we have empirical formulas. There we can use our analytical methods easily. But think of an insulator surface. So what shape actually you will give to the insulator surface? No regular shape can be applied to an insulator surface. Moreover, we have three kinds of coordinate systems, right? The curvilinear coordinate systems. So what are the three kinds of coordinate systems which are available with us? Any idea? What are the three coordinate systems available by which we solve our electric field or any mathematical problems? So what is the most widely used this coordinate system? What is the most widely used? The XYZ coordinate system, what it is called?
Cartesian.
Sir,
Yes?
I think it's spherical.
Cartesian coordinates and polar coordinates.
So Cartesian coordinates is what we are generally using, the XYZ. Normally we use the XYZ axis, right? So that is called the Cartesian coordinate system. And we have another two coordinate systems, which is known as cylindrical coordinate system, and the other is spherical coordinate systems. So first of all, for understanding field computation, numerical field, you need to have a basic idea of the coordinate axis. Okay, this I will come a bit later. we have X. This is our normal Cartesian coordinate system. What are the different shapes we can fit to a Cartesian coordinate system? It can be a rectangle. Any shape which is consisting of linear sides, or what to say, there is no curvature kind of thing that we can appropriately represent in a Cartesian coordinate system. Now suppose we have a cylinder, right? Suppose we have a cylinder like this. Suppose we have a cylinder like this, and if we try to fit our Cartesian coordinate system into this type of a cylindrical structure, we can fit it obviously, but it is not appropriate for this kind of shapes. So for that we have another kind of coordinate system, which is called the cylindrical coordinate system. Okay. So I'm representing it like this only. Okay, in cylindrical coordinate system, we have R, phi, and Z. Like here, what we had in Cartesian, we had X, Y, and Z, right? So here we will be having R, phi, Z. So what is R, what is phi, what is Z? So basically, if you think of Cartesian coordinate system, the best for Cartesian, I'm telling now, okay? So the best you can imagine is your room. Just wherever you are sitting, just look around your room. It is a 3D box, right? So we have three axes. We have a height from the surface. We have a displacement in the this X direction and a displacement in the Y direction. So basically, any point in this room can be uniquely identified by my this what is called Cartesian coordinate system. Any point in your room, there is no curvature, all straight walls, and you have 3 dimensions. Right now, you think of your room as a cylinder. So cylinder, what are the 3 things you need to identify? First is along, suppose this cylinder is there. I am identifying a point, say here, suppose P. So how much it is? So if you imagine a cylinder, if you imagine a plane which is bisecting this cylinder in the midway, so you need to understand this point. How much is the displacement from this middle point? So this is known as R. What is the height of this point from the ground? So suppose if this is my ground level, so what is the height of this from the ground? This is Z. And apart from this, we have another point. What is that? What is the angle of curvature? What is the angle of curvature of this point P, which is represented by phi I? Okay, so that I cannot show here, but you have to imagine it. Just take a, say, some kind of cylindrical box here. If you see a cylinder, right? So if I take any point within this container, say this point within this container, I just the tip of this pen within this container. Now you see there is a displacement of this point from this axis. There is a displacement. It is also lifted up from the ground by a certain distance. And again, along this curvature, we have some displacement, right? So this is like a circle, right? There is some curvature here. At this point, so for this point, the curvature is 0. And gradually, if we move along this plane, we will have a curvature. Okay. So you need to think of this. This is not very straightforward, but you need to think of this. What are the different R, phi, and Z coordinates from different points? So better you can visualize it. You can just think of a cylinder. You can take a container like this I gave. This container, you just put some points inside. put some marbles, some balls inside, and then you can realize what are the different parameters. Means what are the different coordinates by which I can uniquely identify my point. So it is R, Z, and phi, right? Okay, fine. So another coordinate system which is very rarely used is the spherical coordinate system. Spherical, we cannot draw it on the paper. I'll just write it. It is very rarely used. So spherical coordinate system, it will be R, theta, and phi. So this is my radius. This phi is the same as that azimuth angle. Phi is called the azimuthal angle. And this one has a name. I forgot that this name for this azimuthal. One second. Okay, so this is known as the polar angle. So this is very difficult to imagine actually. So if you think of a sphere, just take a ball and you will see any point within that ball, you can represent it uniquely by the radius of that point within that ball, the angle by, there is an angle. There are two different kinds of angle. Just I'll try to explain you if it is possible. Just I'll take my normal Cartesian coordinate. So this is my Z, Y, X. Suppose I have a point here, say P, which is given by R, theta, and phi. So now, if I think of it, you think of this point within a sphere, okay? So now you try to imagine what is my R. R is pretty easy to imagine. So this distance is R. What is theta? It is this angle. One second. This is basically taken in the anti-clockwise clockwise direction. It is phi. And if you think another plane, this angle will be called as theta. It is very difficult to imagine in 2D. You have to see some videos in YouTube. It will be available. That will show you through animation. It will show you what is the difference between these two angles, this theta and phi. Theta is called the polar angle and phi is called the azimuthal angle. Okay, so these are the different coordinate systems. So what I was in numerical field computation. So now you need to understand. I was talking of boundary based and domain based methods, right? I explained why we go for numerical field computation rather than analytical field computation. So in numerical field computation, we have the boundary based methods and then the domain based methods, right? In boundary based methods, we have finite element method. I'll explain what is the difference between boundary based and this domain based methods. Sorry. In domain based, we have FEM, that is finite element method. Then we have another method which is known as finite difference method. And in boundary based, there are many other methods. I'll not explain all. We have charge simulation method and we have surface charge simulation method. Probably in the course in lecture 7, you will have encountered with this term, the surface charge simulation method. And there, professor has presented some results pertaining to the field computation within an insulator. And he has explained the different results. So I'm working on this field computation area actually, and I'll explain you all these methods in details. So if you want, will it be, is it agreeable by everyone if I explain all these methods? Will not be explained in details within within this course. But if you want, I can explain all the methods in details. Is it fine for everyone, or you want to go by the course? You want all these things in in the superficial level only?
No, the general course is done by Dr. Reddy, Varetti.
Yes.
But this is the some exceptions you are giving it. I think very well you can go.
Okay, I'll explain this charge simulation method and the surface charge simulation method in details. FEM and FDM, if time permits, I will try. Okay, is it fine?
This is 736.
Is it fine, Mr. Raju?
Yeah, it's right.
Okay. Everyone, is it fine, Dr. Valsalal? Purushottam?
Yeah, yes, Mr. Chaudhary.
Yes, sir.
Oh, okay. Okay. Okay, fine. Then today I will give you a brief introduction of charge simulation method. So first I need to explain you 1 second. First, I need to explain you what is the difference between boundary-based and domain-based method, right? So for that, I need to give you an example. So you think of it, think of two electrodes which I was talking about, right? And I have another electrode. So I suppose, don't assume it as a perfect circle. If it is a perfect circle, somehow we can try to do it. You can tell we can do it by analytical method also. We can fit it in the spherical coordinate system. But no, just think of it as a numerical field computation problem, and we'll try to apply one of our numerical field computation techniques. Okay. So suppose I want the P at P. Suppose it is of a particular XYZ coordinate, and we want the field here due to this electrode system. So the first thing which you can do, so in boundary based methods, that is charge simulation method and surface charge simulation method, what we do is the first step in, okay, first before going into that, I need to explain something more. Otherwise, so in numerical field computation, the basic philosophy of numerical field computation is there are different steps involved, right? Step one is identify the appropriate coordinate system to solve the problem. First, the first and foremost step is based on the geometry. You need to identify which one out of Cartesian, cylindrical, or spherical is the most appropriate coordinate system to solve my problem in hand. Okay. So the next step that will involve identify the governing equation. Identify the governing equation or equations. There are different field governing equations. Like if it is an electrostatic problem, then we have what are the different governing equations in the electrostatic case? Can anyone tell? What kind of field we observe in electrostatic case, where we do not consider the time variation of electric field and the generation of magnetic field and all those things. If we just consider the electrostatic case, what is the governing equation, the main governing equation? Any idea? Okay, so the main governing equation, I'll explain it again. In case of electrostatic, there are two governing equations. One is Laplace's equation and the other is Poisson's equation, right? So what is Laplace's equation? Can anyone tell what is Laplace equation? It is del square phi equal to 0. Phi is my potential. Del square operator is the Laplacian operator, which if it is in the Cartesian system, it can reduce to dou square phi by dou x square, dou square phi by dou y square, dou square phi by dou z square. 0. Okay, so this is my Laplace equation, and this right hand side, it is 0 here. And in Poisson's equation, you will see del square phi equal to some minus q. This is the free charge. This is the charge in the this boundary. There are two dielectrics are there, and if there is any charge trapped in the what is called in the boundary of the two dielectrics, if there is some charge trapped, then we use the Poisson's equation. Otherwise, we use the Laplace equation. So this is the second step. Okay. Identify the governing equation. The next step, discretize the geometry appropriate. What is meant by discretizing a geometry? Any idea? What is discretization? What is
Dividing the
discretize?
area.
Yes.
Yeah, dividing the area into small triangle or anything.
Yes. Why we do that? Anything you can think of? Why we discretize the geometry? Why we divide the entire geometry into smaller triangles or quadrilaterals?
Yeah. Field is available in all the places. No.
Yes.
In that boundary.
Why we do that? Any idea?
Yeah, field is available. That's why we are doing.
Yes.
Yeah, field is available.
Field is available means?
So that
not-
defined area.
Fine. I'll give you one example. You tell me this one. Suppose I have a geometry like this, say an ellipsoid type of geometry. Okay, fine. Not this one. Say I have a okay. So not like this even. Then irregular geometry. Say I have something like this. Some geometry I have like this. Then you are saying I will divide it into smaller triangles or quadrilaterals, right? Is that what you are telling?
Yeah.
So we have discretized it into different quadrilaterals. Okay. So now if you just divide these quadrilaterals, you can get some triangles. Okay. You do it for the whole thing. So now the problem is why we do this. First, you need to understand why we do this. Because this is an irregular geometry, right? We cannot apply any of our governing equations to this kind of geometry. So we need to discretize it into smaller elements where we can individually apply our governing equations. To apply any governing equation, we need a well-defined geometry or like a rectangle or a triangle, like that kind of thing. So that is not possible within this irregular or undefined geometry. So that is the main reason for discretizing or dividing it into smaller rectangles or smaller sections. This is in the 2D I am telling. So in the if you have a 3D thing, if we discretize a 3D figure, we will instead of triangle we'll get prisms or pyramids. Instead of quadrilaterals, we'll get parallelopipes. All those things we get. That is a different thing. So coming back, we discretize it. Okay, fine. We have discretized our geometry. Now how do we proceed further? So next step will be apply your field computation process. So this part will vary for all different process. CSM search simulation method, it will be different. FEM finite element method will be different. Finite difference method will be different. Apply your field computation algorithm. Okay. So here what we have done in this particular irregular figure which I have shown, this one, we have discretized the domain of the system. That is the volume of the system. If it is a 3D figure, or a 2D, if you say a sheet, you just take this mobile phone, this surface. I just discretize this. So this is my domain, right? And what is my boundary? My boundary is this one. These four sides are my boundary. And what is my domain? My domain is this one, the inside thing. So if we discretize the domain, then it is called the domain based method. And if we discretize only the boundary, it is called the boundary based method. So now you will be thinking that this boundary is only a straight line, right? How will you discretize? Yes, it is not this usual discretization. It is not like the discretization which we employ in case of domain based methods. Or yeah, so in the boundary based methods, what we will do, suppose as I was showing you my mobile screen. So basically we will discretize this straight line. Suppose I discretize it using, how can you discretize a straight line? It will be with points only, right? So suppose this is my electrode and I am applying high voltage here. So the charges will be deposited on all these boundaries, right? So these charges I am trying to discretize. So this thing, this line, I am representing it as a union of point charges. So these are all point charges, Q1, Q2, Q3, dot, dot, dot. Here also we have all Q and all this, all are point charges. So if we can do this thing, and suppose I have my high voltage electrode like this and my low voltage electrode also like this. Again, we discretize it into different point charges. Then if we want the field, say here. So if you know, using this charge simulation method, this is the basic thing. We discretize the boundary into, say, discrete charges, discrete point charges or discrete line charges. And then once using this charge simulation method, the main goal will be not to find the electric field. It will be to find this unknown discrete charges. And if then what is the ultimate goal? We have to find the electric field. So if you want the electric field, say at point P here, you can obviously you can take the field due to P, field at P will be due to all these imaginary charges. This Q1, Q2, Q3 doesn't exist. But for the sake of simplicity, for the sake of simple field computation, we have assumed the boundary to be made as a union of point charges or a union of line charges. And we apply this to find the field at a point P. So what will be the field at point P if there are only two charges, Q1, Q2? It will be the field due to Q1 plus the field due to Q2. Obviously, due to all these things. So what will be the field at P now? It will be the contribution by all these imaginary charges, or which we call the simulation charges, due, at P. So this is the basic philosophy, or the basic, in short, I have described you. So next class, I will be starting this charge simulation method, and then I'll go on to its further enhancement, which is the surface charge simulation method. Okay. So today, if you have any doubts, last 10 minutes, you can ask me. You have to ask some doubts. Any questions, any doubts, anything you can ask.
Yeah, one question.
Yes.
Yeah, when we say dielectric strength, the term, and the material strength, both are same or different?
Yes, can you tell once again?
Dielectric strength and material strength.
No, obviously, material strength, it is a vague word actually, because it is not a scientific word. Dielectric strength, it refers to the dielectric strength actually. So that is the strength of insulation. But material strength, by material strength, if you mean dielectric, it can be dielectric strength, it can be the mechanical strength of the material also. So material strength is basically more generalized version, you can tell.
Yeah.
It is not the same as dielectric strength.
Yeah, okay. Thank you.
Okay. Any other doubts pertaining to the course?
Sir, when we are talking about this type test and the
Yes.
sample test, so the tests carried out in the sample tests, are they covered under the type test or no?
No, all tests are different.
That means whenever we are doing a type test of some new equipment or a new thing, so why don't we include the sample test also into this?
Together, how can you do? There is some the standards are there, standard procedures are there which you have to follow. The IEC standards are there. You cannot do it like that. First, you have to complete your type test. Then only you can go for the sample test or the routine tests.
Okay, okay.
Anything else? Any doubts?
The sample test and the routine test, it is all the cost of the test it will be very low, whereas the type test cost is very high.
Okay.
So for a type test is better, we have to spend it in lakhs and lakhs.
Okay.
Whereas a small routine test, it may not cost much.
Okay. Anything else? Any clarification? Anything? Any discussion is required? Anything?
Yeah, one more question.
Yes.
For insulators, we are doing repeatability, reproducibility. But the third one, representativity, are we doing or not?
No, that's what I was explaining. In India, actually, there are very few labs which can actually do your representativity test. And I don't think presently everywhere we are able to do it because this duplication of the field conditions exactly in the laboratory is very difficult.
Yeah, duplicating field condition means whatever is happening in the field, you are trying to simulate and exist in the laboratory, right?
Yes, correct.
So if you take pollution, that is going to be non-uniform. That non-uniformity may not be able to do. I mean, we make it in the laboratory. That's a problem, I think.
Yes, correct.
Okay. But in that case, what about the reliability of our insulator? Is it okay or not?
Actually, you cannot, even if you don't do it for the actual condition, even if you do it for, say, there is a tolerance band of that also, that is fine. We are going on with that only.
Okay.
Yeah, more accurate. Obviously, we need to do the representativity test also, but we are bound by whatever is available to us, right?
Then the insulator, I mean, first lecture, we had some insulator design, leakage distance. That for problem is given some B, C, D, and all given. But I think it's in the 230 kV system, the values are not given.
Yes, you had told, right?
That range within the range it's given, but correct. But for learners, it may not be. They'll be finding difficulty to what is the actual value.
Okay.
Similarly, for lightning overall, yeah.
Can you just put it to my professor because he has? I'll type my mail ID here, or my this WhatsApp I will give you. If you want, you can just type what is your query and type your name. I'll forward it to my professor Subhareddy. Will that be fine?
Yeah, it's okay. What is your number or not visible?
I have given it in the chat box. You can just note it.
Okay.
Anything else? Any clarifications? Anyone? Any clarifications? Anything?
From my side, it's okay.
Okay, fine. Thank you. Thank you for your suggestions, sir.
Good. You are, I mean, it's very pleasure to listen your lecture.
Okay, thank you, sir. Okay, you are presently working anywhere?
Myself.
Yes.
I am working.
Your professor?
Yes, yes.
Where? Can I know?
Anna University.
Okay, Anna University, Chennai, right?
Yeah, yeah. I'm not basically high voltage engineer. I'm power system, but I have done some work in the surge arrestor.
Okay.
So I'm taking the classes with respect to this, UHV transmission. But
Okay.
this time expecting anything to be learned more. Simply,
Okay.
not without read. By listening itself, I can update something. So,
Okay. This field computation you are liking, or is it?
no, I actually I use the packages, but in depth I do not know actually.
Okay. Okay, I will describe. I'll try to explain as simple as possible.
Yeah. Okay. A short
Thank you.
period, no, it's very difficult to. Yeah.
Yes, yes, yes.
Yeah, go ahead. Okay.
Fine. Thank you then. I'll close the session for today. We'll meet on next Saturday again, 6 p.m. Thank you, everyone. Thank you.
Okay, sir. Thank you. Thank you.
Okay, thank you.
Thank you.
Thank you, sir.
Thank you.